The third learning objective in section 3.5 is to check appropriate conditions for performing hypothesis tests and computing confidence intervals using the z-distribution for inference about a population proportion. Here's an example. A survey based on a simple random sample of 2,293 adults in the USA, aged 18 and older, conducted by a reputable polling organization, found that 406 have donated blood in the past 2 years. Verify that the requirements 1 through 3 below for constructing a confidence interval about P, the proportion of adults who have donated blood, are satisfied. Here are the requirements for computing a confidence interval for the population proportion. First, we need random data. So either the sample needs to be randomly selected or a randomized experiment needs to be performed. We need independence in our sample, which we can check by verifying that the sample size is less than or equal to 5% of the population size. If our sample size is too large relative to the population size, then the individuals in the sample cannot be assumed to be independent. And then we need to check that n times p hat and n times 1 minus p hat are both at least 10. This is slightly different than the condition that we checked for our sampling distribution to verify that the sampling distribution was approximately normal. There we did n times p and n times 1 minus p. But here we can't do that. Our purpose is to check the conditions so that we can do inference about P. I don't know what P is, which is why I'm going to perform a hypothesis test or compute a confidence interval. And so I'm going to use P hat to check whether that requirement is met so that our sampling distribution will be approximately normal. So let's look at this example here. Do I have a random sample or a randomized experiment? Well, yes, it says that it's a simple random sample. So I have a random sample here. Next, let's check our sample size to verify that it's less than 5% of the population. Well, our sample size is 2,293. I don't know exactly how many adults there are in the USA, but I know that 2,293 is less than 5% of all of those, and so I do have an independent sample. Next, I need to check n times p hat and n times 1 minus p hat. I can do this calculation pretty straightforwardly. My n is 2,293, and my p hat would be computed by dividing 406 by 2,293. Well, you'll notice that the 2,293, I've got one in the numerator and one in the denominator. So those will cancel out each other, and I'm left with just 406. And that is greater than or equal to 10. And now I'm going to do the same thing, but I'm going to do 1 minus my p hat. And I could do this in GeoGebra. Let me just pull up a GeoGebra calculator screen. And I'm going to do 2293 times 1 minus 406 divided by 2293. So there's my n times 1 minus p hat. Whoops. And I'm going to hit equal, and I get 1,887, which is also greater than or equal to 10. So therefore, I have met all three conditions for computing a confidence interval for the proportion. Let's look at the next example. This is the same situation, but now it says verify that the requirements are satisfied for testing whether P, the proportion of adults who have donated blood, is less than 20%. So now I'm going to do a hypothesis test. The first condition is exactly the same. I need random data. And so this is still the same thing as it was, which is that I have a simple random sample. The second condition is also the same. And my sample size is still the same value, which I need to be less than 5% of the population. 2293 is my sample size, is still less than 5% of all adults in the USA. Now, to check my n times p conditions, and n times 1 minus p, I'm going to use, instead of p hat, I'm going to use p sub 0. P sub 0 comes from the claim proportion. So in this example here, the 20% is the P sub 0 that I need to use. In a hypothesis test, we assume that the claimed proportion is true when we check our conditions or our requirements. So let's check those things. I need my n, 2293, times now 0.2, and I get 458.6. So my n times p sub 0, I'll just put the values in, 2293 times 0.2. That was 458.6. Which is at least 10. And we'll check our n times 1 minus p sub 0. So 2293 times 1 minus 0.2. And that equals 1834.4. Which is also at least 10. So again, I have met all the conditions I need for performing a hypothesis test for the population.